I think hopefully we're back. Great. Is it going haywire, Ankit? Yes. Okay. That's kind of creepy. Okay. Oh gosh. Well, at least it's being recorded. All right. So maybe we pause.
You just click over here on this one.
Yeah. Do you wanna fix this?
No, just one sec.
Do you wanna do this?
That should work.
Okay, that's fixed. Okay, everyone. Thanks for Ankit. And okay, cool. So I will try not to do that again, unless people fall asleep. Then I will do that, and I'll make that full screen so you get the full effect. Okay, so I'll try not to write near the top too much. So all subsets takes 2 to the n. So if you want to just say just the subsets of size, say 3, maybe only subsets of size 3, then they're going to be roughly n cubed of these. Right, but if you're Amazon, I don't know how many products they have. They probably have over like 1 million products. You can't do something of size n cubed. You can't search over all of these. Right? You could think otherwise. I could just say let's just kind of think of having a counter for each of the product pairings, and we can, every time something happens, we can run like this streaming algorithm from before and keep a counter for these. But this becomes combinatorially too big. So doing this becomes hard to do. We don't want to keep a counter for all of these. So we're going to, instead of the streaming algorithm made kind of one pass over the data, we're going to kind of get around this by making a few passes over the data. Or we don't even have to do it over the, so a few passes over the data, and this will allow us to get these more complex, complex relationships. Okay. All right. So let's talk about this a priori algorithm. Okay. And so this is like a really heavily cited algorithm inside data mining. And there are probably hundreds of papers written on extending this in various ways. So there's a paper I linked to in the notes. You can read more about it if you want to. So the idea is to make a few passes over this. And so the idea is that there's simple idea that if item set, and let's say this is let's say that all of my items, so you just don't have to, it's a little bit more illustrative not to use numbers, are like S1, S2, up to S, maybe this is Sn, right? So if item set Si and Sj is frequent, and by this I mean occurs at least epsilon m times, then both just Si and Sj then both these individually also have to occur at least epsilon m times. Okay, so if this item set occurred a lot, like if I went back here to this small example, because 1 and 2 together occurred a lot, it meant both 1 and 2 individually each had to occur a lot also. Okay, so then the idea is then you make a first pass, and on this first pass you find all items which are occurring at least epsilon m times. Right? So you want to find all the individual items. Don't worry about the sets yet. First find just these individual items which are doing this. And if you want to do this, if you don't want to, so you can either keep track of, so you can have, either you can say that there are n counters. So if you're Amazon, you probably have space for all n of your items, even though it takes a lot. Or you can do something like you can do something like the Misha-Gries algorithm that we talked about last time, and this will find all of the heavy enough items, and it may have some false positives as well, but it won't have too many false positives. Right? So I know that if I only care about things that occur at least epsilon m times, I can't quite, so with the Misha-Gries, I could guarantee that there are at most 1 over epsilon of these. Right? There are at most 1 over epsilon of things that occurred at least epsilon m times. Otherwise, I wouldn't, there wouldn't be enough space for each of them. Now, that's not the case here. That's not the case because I can have multiple things inside of each of the baskets. So I can't say that each occurred at most epsilon 1 over, like there are most 1 over epsilon things that have this counter. But I can say something like if the maximum size of the basket is bounded, so say that max over ti is equal to, let's say 100, then there are at most 100 over epsilon of these items I'd have to keep. And this only depends on this maximum size and this epsilon factor that I have. It doesn't depend on the initial size n. Right? So this, I would say, is n1. So this is the number of items I found after the first pass. So I read over all my data, I keep track of all the counters, and I only keep the ones that have size that occur at most epsilon m times. And I can do this approximately using Misha-Gries or something else. And I know that the maximum basket is bounded, then I only have at most 100 over epsilon of these possible things. If you don't have, often, there may be some outliers. Someone goes, maybe you've seen these weird people at the grocery store who buy like 10,000 things of pudding or something like that, right? So they have lots. Occasionally, someone has lots of items. So this, if you look at the true maximum, it's probably not a great bound. But and you could probably look at something like the expected value, and that would give you a pretty good kind of assessment of probably how many, the most you could possibly have in these things. It's probably much smaller than this. This is a kind of a strict upper bound. In practice, this set that you keep is going to be much smaller than the original set. You can only build these relationships if you have, if you have enough statistical evidence of this. So this would be much smaller. Maybe you don't want to give a full fraction. You want to say, I only want to look at things that have occurred at least 20 times together. I don't care what percentage of my full data set this has. Well, then you can't quite get a bound like this. You can just, you may have all the items that have occurred at least 20 times. So that may not help filter too much. But let's assume that you set some sort of threshold of how many times it occurred, and you just kept track of these ones that occurred at least this fraction number of times, and this is a smaller number, n1. Okay? So then what you do is you build all n1 choose 2 of these pairs of the items which survive this first round. So you find all the items which have survived this first round, and you get this set of n1 of these items, and now you build these n1 choose 2 pairs, right? So this is now about n1 squared over 2, roughly, right? So you're getting about, and now instead of, if you looked at all the items, all the pairs initially, you get n squared. Hopefully n1 is going to be much, much less than n, and typically this will be the case. So then you only look at these pairs here. And so then you make a second And so let's call these are the set is going to be P, is going to be the all pairs left. So all the pairs that are remaining. So you make a second pass, and so now in the second pass, find all pairs which occur at least epsilon m times. Right? And so again, hopefully this size is now much smaller, and you can either do this in memory or you can run Mischigrees over this. And so this will again give you just the pairs which have lasted. Right? So now if I want to find triples that occur together, I know it has to, each of the sub pairs must also have occurred together. So once I found these pairs, and I know all the pairs I found are all the interesting pairs, because if there was a pair that it would have required that both of its individual elements had occurred a lot if this pair occurred a lot together. So then you just kind of keep repeating on remaining on, let's say, all right, on k-tuples with each k minus 1 subtuple that was surviving. Okay, so you can kind of repeat this process over and over again, and you'll guarantee to find everything doing this. But you're pruning the search very effectively. So it's kind of a clever way of pruning this. Okay, hopefully you kind of get this. So how about I go through kind of a more complex example in order to do this? I want to. Examples are kind of slow to write on the board, so let me try and copy and paste something from my notes. Okay, and we'll kind of go through this. All right, so hopefully you've all found all the notes on this stuff. Okay, let's see if I can. So work. Okay. All right, so it only gave me, uh-oh. Okay, that didn't work so well. Let me try. Okay, I'll just try drawing on top of the notes then. Okay, so let's look at this example. So we'll look at this example here. And so let's go through this example. Okay, so these are, as you can see, that there are these 12 baskets here. So in this example, we have m equals 12. And these sets range from 0 to 9. So n is going to be equals 10. Usually I start counting from 1. In this example, I start counting from 0 for whatever reason. Okay, so on the first pass through here, what we'll essentially keep a counter for each one of these items. And a 0. Okay, and so as you would do this, you'd actually make a stream and just update the counter, but that's going to be a little bit tedious. So let me just go through and we'll count all the ones. 1 occurs 3 times. 2 occurs 1, 2, 3, 4, 5, 6, 6 times. 3 occurs 1, 2, 3, 4 times. 4 is going to occur 1, 2, 3 times. 5 once, twice, only twice, 3 times. Where's the, oh, yeah, I see it. Okay, great. That's, oh boy. All right, well, you know, sometimes you need a, okay, so how many times do we see 4 again? 3? And 5 occurred 3 also. And then so 6, 8 times. Okay, 7 occurs 3. No, 4 times. 8 is occurring twice. 9 is occurring 4 times. And 0 occurs twice. Okay, and so now we're going to set our threshold. We'll set epsilon equals to 1/3. That's from right here. Epsilon is 1/3, so that means I only care about things that occurred at least, I think they had to occur at least 4 times. Okay, so the ones that I keep are going to be 2, 3, 6, 7, and 9. Okay, and so then so I'm going to keep these into the next round, next pass on here. But to do that, I need to write down all of the interesting pairs. 2, 3, 2, 6, 2, 7, 2, 9, 3, 6, 3, 7, 3, 9, 6, 7, 6, 9, and 7, 9. Okay, and let's see if any of these pairs now occur at least at least 4 times. And so now I can go through and check this. And let's see. So we have 2, 3 occurred here. And that's it. So I just get one instance of this. 2, 6 occurred together. This one, 2, 3, 3 times. 2, 7 occurred once. Looks like just once. 2, 9 once, twice. Occurred twice. 3 and 6 once, twice, 3 times. 3 and 7. Looks like it did not occur. 3 and 9. Nope. No, is there one here? One there. All right. Don't forget about this one, right? 6 and 7 occurred once, twice, 3 times. 6 and 9 occurred once, twice, 3, and 4 times. And 7 and 9 once, twice. Okay? So once we've written this down, there are 2 things there are 2 things here that we should kind of just observe. Is that could there be any other pairs that I did not count explicitly, which occurred that occurred 4 or more times? Like, it can't possibly be happening because it would have had to have used some number 1, 4, 5, 8, or 0, which we know that self didn't occur at least 4 times, right? Every one of these pairs occurred. Okay, and so so then the next thing is the only thing that survived is this one here. 6 and 9 occurred together 4 times. So could there be any triple that could occur together 4 times? Is that possible? No, so that's not possible either, right? So the only things we get, the outputs are 2, 3, 6, 7, and 9 individually, and 6 and 9 together are the only things that we saw at least 4 times. And we can do that. We can stop this search already, right? So if we'd had 6 and 9 occur together, and let's say, and 6 and 7 occurred together 4 times, but 7 and 9 only occurred together twice, would it be possible to see something that occurred 3 times again? No. So if you were to consider, if I were to go another round and I'd say that 6, 7, 9, and I wanted to do a counter for here, I know this could occur at most twice. I know it occurred at most twice together. Let's see. It turned out 6, 7, and 9 occurred here and here. So it actually did only occur twice. But I can know it occurred at most twice because it contains 7 and 9, which only occurred twice. So I can stop the filtering process already. And so when you do this, you often have much bigger things than this. But you can see that by doing this filtering, you kind of expand out a little bit, but then it shrinks, it prunes it very quickly. There's kind of this nice way of looking at this where you can think of having, this lattice structure. Well, let's say that my set was just 1, 2, 3, 4. Let's say 5. And I can think of having this lattice, and the empty set really isn't that interesting. But then I can say that I have these smaller sets, 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5, right? Okay, and then, okay, my circles are getting bad. And then I can have next sets down 1, 2, 3, 1, 2, 4, 1, 2, 1, 2, 5. If I keep going this, are there going to be more or fewer than the previous row? And it turns out it's going to be the same. So 1, 3, and we'll see this in count. 1, 3, 5, 1, 4, 5, 2, 3, 4, 2, 3, 5, 2, 4, 5, and 3, 4, 5. So the number in this set is going to be 5, choose 2, and this is 5, choose 3. And because 5 minus 2 is equal to 3, then these are the same number, right? Right. And then I go back further. All right, so I can, instead of write them which ones are in, I can say which ones are not in, and that's still 2, right? So then if I go back down, I can write 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 4, 5, 1, 3, 4, 5, and 2, 3, 4, 5, and then at the bottom 1, 2, 3, 4, 5. Right. So now, as I started to at the beginning, I can draw these lines of dependence here. So this 1 has dependence to these. 2 has dependence to these guys. 3 has dependence to this guy over here, and my lines are going to go crazy. Okay, so and then you can keep drawing this further down. So 2, 3 occurs here. It occurs there, and there again. Right? So you can see that there's this dependent structure going down, and so what happens is that if I kind of say that this 1 does not occur very frequently, then it goes down this chain and it knocks out this one, this one, this one, and as well as here, here, So all of these sets get knocked out. Once I know this is, I can kind of prune a huge section of this lattice all at once here, right? And so this becomes a very effective way of pruning by thinking of it in this class structure. You don't ever want to expand this. You can see that, and so then as you're doing this, you're kind of fighting against. You're doing more expansion as you go further down, but the pruning gets more effective. And usually after a round or two, it becomes more effective at pruning. Okay, so this technique is useful in doing these item set analysis. If you're doing things, I don't think we'll talk about this in this class, but there's this classic problem on social networks. One of the things you want to do is count the number of triangles inside this large social network. This turns out to be kind of an interesting quantity. And to kind of count this number of triangles, you want to create these higher level structures you might find within this graph. You kind of want to do this other similar kind of partwise expansion, where I kind of want to do a lot of pruning instead of checking all possible things whether a triangle exists. I kind of want to build them up incrementally. And you kind of think about these in a similar light by thinking of this as a lattice and kind of only expanding the search as you need to. Okay, so all right, so that's kind of all there is. That's all I was going to say about this item set mining and these a priori things. Oh, I guess one more thing. Let's go back to this picture here. So if you look at this, you want to kind of use this set 6 and 9 to kind of maybe do some sort of prediction, and you'd kind of see that 6 occurs more than 9, but every time it turns out every time I bought, so if these are items, every time someone bought 9, they also bought 6, right? So for every because the number of times you purchase 6 and 9 is equal to the number of purchases of 9. So that if you know they bought 9, you can kind of predict that they should buy 6 as well. And you can kind of infer these, trying to kind of maybe claim there's some sort of causal relationship here or something like this. These are often useful in predicting what's going on. And it's a way of kind of understand these more complex relationships. Yeah?
It seems like this works really nice with this well-defined item space. If we have a less defined space, like language or something, where you may not be able to enumerate all the possible things you can encounter. You just kind of build as you win.
Yeah, so this works, just to repeat the question, this works with these nice defined items like products in Amazon, but with language. So there are a couple things you can do. You can think of these, you can break these individual items down to be like these individual k-grams over the characters. And then you kind of see where things work together this way. And then the number of, say, 2 grams for characters is still not that big. Even the 3 grams is not too big, and you can kind of do something like this. The other thing you can do with language is you can kind of cluster together some words and trying to use that to build relationships. So there's this kind of common technique, and there's software to do this that does this technique called stemming, and that's like turning words into like their base words. So like if you say loved, this would be stemmed into love, and so loves would also go to love, right? So these are you say these are the same words. So if this co-occurs with something, it might co-occur with something else. Now that kind of factors out some of the grammatical structure, but this kind of reduces down your set in some sense. This would be useful if you're like saying instead of Obama, you have Obamas with an apostrophe S, right? So now these are probably, the concept is the same in both of these. So this is where it'd be useful to kind of group these two things together. And maybe you'd use something like the stop words to somehow find the interesting items. There are different ways you can kind of reduce the set down to something more manageable. But when you're dealing with these complex grammars, either just you have a much bigger domain n, or you kind of have to, so sometimes you can still do that. There aren't that many words in the English language. What is it like? Maybe it's like 100,000. I don't know if that number is after stemming or is before stemming. But even, let's say it was after stemming, how many variations of words are there? So maybe a word on average has 10 variations. So maybe that's a million. That's still only a million different words. You could maybe run this with a million words. So you might still be able to do that. I don't know if someone's done that, but I'm just that's kind of what I'm guessing here. Yeah, it's an interesting question. Okay, so any other comments or questions about these frequent item sets? Okay, so let's kind of switch topics here a little bit. And so let's talk a little bit about these Bloom filters. And so a Bloom filter is going to kind of be an interesting kind of take on, it's kind of a variation on a hash table, which the count min sketch was another kind of variation of this. And so this is a structure to keep track of sets. So you want to keep track of sets. Okay, and so it's not, the count min sketch gave you an estimation of the frequency. This just tells you whether something is in the set. And so these come up kind of, these count min sketch and the Bloom filter and various variations of these, these are kind of building blocks that you use to kind of do other sorts of analysis. You find these inside of routers and so forth, keeping very basic statistics, but very efficiently and with a lot and very small space. And so instead of counters here, the Bloom filter is just going to use kind of bits for the individual entries instead. Okay, so it's going to keep track of a set S, and basically the properties it's going to have is if X is in S, it will can't spell wise. It will always return true. So if you have a query, is X in the set? It will always return true if it is in the set. And if X is not in the set, so if is not in, it will rarely, okay. It will rarely return true. So it'll usually return false. So it will have no, that means it'll have no false, so of no false negatives. So it'll, if you want to say something is in there, and it is in there, it'll always tell you correctly. It will have some, it's going to have some false positives. So it'll sometimes say something's in the set when it's not there. If you want to do this, exactly, you're going to probably need a lot more space. You're going to need to use these standard hash table. But if you're allowed to have some false positives, then this is going to be okay, right? So one example where I saw variations of this being used in a router is that they're trying to keep track of some kind of packets which they identify as like some sort of spam packets, and they want to do a quick filter. And so it's okay. They don't want to miss anything that's known as spam, but occasionally something will be a spam, and so they're not going to just mark it as a spam. At that point, they're going to go run a more expensive filter to go check. And so if it really is spam, it doesn't matter so much how long. You aren't really delaying something useful, but you occasionally delay things which aren't spam, but you'll eventually resolve these more carefully. Okay, so we're going to build a data structure with these properties, and it's going to be randomized. It's going to use hashing. Okay, so this makes sense what this is doing, right? So if my data set was small, I would just use a standard set technique that can answer this exactly. But if it's very large, I want to be very efficient, then the Bloom filter or some variation of it is often what's used. Okay, and so let's go and okay, so the idea is I'm going to have I'm going to do this with I'm going to have this table B, which is going to look like this. All right, and so forth, and it's going to have M bits. So this is from 1 to up to, this is location M, and so initially all say bi is equal to 0. So all these values are set to 0 initially. Okay, and so then I'm going to have k different hash functions. And so again, this is a random hash function, not locality sensitive. And so these hash functions should essentially map to a random location in this array. It'll give me a random number between 1 and m. Right, so each hash function, hash I, is going to go from my input domain to a random number between 1 and m. Okay, so I'm going to see a bunch of items, and maybe it's some header of a packet or something, and I'm going to map it to one of these places in this array. But I'm going to have k of these hash functions, more than one. But I only have one array. In the count min sketch, I had k hash functions, or t of them, and I had t different arrays. Now I only have one array here. Okay, so what's going to happen is I'm going to have this, and so let's draw this out here again. And so for each of the hash functions, so as something comes in, so I'm going to have some number, some value that comes in. I'm going to send it to each of the hash functions, and then the hash function will map it to a random location and to make sure that the bit is set to 1. Okay, so it'll map to these random locations, and it's going to set the bit to 1. If it was already 1, it keeps it a 1. If it was not a 1 before, it's going to be set to 1. Right, so you can write this for x in my set. I'm going to go through, and so for j equals 1 to k, I'm going to set b, this array, hash into the array with x, and I'm going to set this to 1. Okay, so each value causes all these locations to be set to 1. Okay, so this is all you have to do to put stuff into the set. Now, how do I answer, if I go back, how do I answer this query? Is x in the set after I've done this? If what? So how would I answer it? If h of x is equal to 1, but I have k hash functions, so which one do I use? I'll just use all of them, yeah. So you say, so on output, you say x is in S, if and only if all h of I of x is there b entry this is equal to 1. So if all of the bits are set to 1, it's in the set. If any of them is 0, it couldn't possibly be in the set. Okay, so it's a fairly simple idea, but usually in a hash function you just map it to one location. Or maybe you do these extra tricks, like you do this cuckoo hashing where you map it to 2 locations. You always check 2, and if either of them, you you load it in one of the locations, but if one of them is full, you map it to the other, and this allows you to pack hash functions more, hash tables more densely. But again, you're only storing in one location. Now I'm storing it in k different locations, but I'm not actually storing the value. I'm just putting a single bit in there, right? So if my number of items in my universe is very large, I may not want to store log n kind of a full word of information, a full byte or a few bytes to store the actual items in there. I just want to store a bit. This can save me, this can really compress it much more. And often the size k, the number of bits, hash functions that you need is going to be much less than the size of the word. Or at least it'll allow you to pack this much more. Okay, so this will work where and kind of the rule of thumb for how. So one of the questions you should ask is, how large should you use for k? What value k should you use? So if you use larger k, what's going to happen is that you're going to fill up this this array. You have limited space. So if you use k is equal to the size m, maybe m is 1,000, and use k equals to 100, you're probably going to overfill this thing. And the only thing you're going to have very few zeros left. So you're going to have a lot of false positives. If k is too small, then you're going to also have a lot of false positives because you'll have a collision, and you'll see too many of these. You'll too easily find these collisions. Okay, so the rule of thumb, and we'll kind of I'll go through a kind of a pretty close analysis of where you get this from. Of thumb is to set k equals to the best way is roughly going to be m, which is the size of this array, over the size of the set times the natural log of 2. Okay, so now the problem is you don't necessarily know the size of your set. So you kind of want to, if you knew that, this is a number of distinct things, right? So what you could do if you're doing this in a stream, if you knew the size of your set, then you can do this. If you're doing this in a stream, you don't know how many distinct things, because if I get the same item coming twice, the hash functions will map it to the exact same locations, right? So this doesn't account against the size of the set. So if you're doing this in a streaming elements, then you may not know this, but if you know the size of the set, you can set this. If not, you may estimate, or maybe you can try and keep another way of estimating the total count, and then kind of update the size as you need to. Yeah.
Can you clarify how k being large also increases the false positive?
How k being large increases the false positive. Okay, yeah. So let's just go through and like a very small example here. Let's say that m in this case was equal to, let's see how many buckets I can draw. 1, 2, 3, 4, 5, 6, 7. Okay? So in this case, m is equal to 7. And let's say I set k equals to 4. Okay, so I put the first item in, and I said this bit, this one, and this one equal to 1. I put the second item in, and it says this one is 1. It was already 1. Well, I'll use a different color, right? This one is 1, this one is 1, this one is 1, and this one is 1, right? So now I go and check a third item, and I check, okay, I want this to be 1, this to be 1, this one, and this one, and yeah, because only way is if it happened to hit this empty cell here, right? So if you overfill it, and if I had k equals 5, it'd be even worse, right? I probably would have filled them all to be 1. So in this case, I'd probably want k to be equal to 2 or something. It's a small example, but you can imagine as you get bigger, the same sort of thing occurs. Yeah. Right. Okay, so let's kind of see kind of why this works. Let's kind of, it's the analysis is not, at least a rough analysis is not too complicated, but I think it's kind of illustrative of what's going on here. So, so the idea of a hash function is that it's going to map to a random cell. So if you write down 1 minus 1 over m, this is the probability that that's some, let's say some bi is not set to 1 by a single point x in S and hash h of j, right? So for a single point and a single hash function, this is the probability that it's not set to 1. Okay, so then you say if you're doing k of these hash functions, and these are independent, so sometimes a single element will hash to the same location. So I can just, they're independent, so I can take the product of these. This will be the probability that some individual cell is not won by a single x in S and k hashes. So if I do k independent hashes, then the probability that the bit is not set to 1 is now 1 minus 1 over m divided by k. Right, and so now let's say I'm going to hash, so now I want to say the probability some element is not won by n objects. So we'll say n, this is equal to the size of S, and k hashes. So now this is going to be 1 minus 1 over m to the k n. Actually, this error is this step is slightly wrong. There's going to be some similar things happening when the hash function gets really full. This is not going to be quite right because of some weird dependent structure. But let's assume this is basically right. Each of the n objects, because the hash functions are kind of, how they affect them are going to kind of be independent. So you're going to kind of have k times n different things being thrown randomly in here. So for one bit, just looking at one bit in this table, this is the probability it's not set to 1. So a very large number taken to, or a number very close to 1 taken to some large power. Okay? So, and then you can say 1 minus 1 over m. This is equal to the probability that b of I is equal to 1 by n objects and k hash functions. And so then if you're going to get a false positive, so now let's look at the probability of a false positive. So that means I'm going to put a new element into k locations, and I need all of the bits to be set to 1, even if that object was not put in there before. So now I can say I want to say the probability of a false positive. So this is going to be 1 minus 1 over m to the kn. So this whole probability taken to the power k. I need k times to hit this bit that was set to 1. I need to do that k times independently. So I can take the product of k of these objects. Okay, now this thing is kind of mysterious here. There's this trick you can use where you can set this equal to basically, it's roughly equal, not exactly equal, to negative k, let's see, kn over m. Here, where this is e 2.71 for there's this trick that the limit as, say, t goes to infinity of 1 minus 1 over t to the power t. Let's see if I got this right. This is essentially goes to e to the minus 1. Yeah. So then this m down here goes to a 1 over m here. And so that's how I end with an e. So I can take out this weird term here and replace it by 1 to the e minus something. Okay, so this is a little bit easier to do. So then this is the probability of a false positive. So I can kind of write this down in a pretty good closed form. I can figure this out. So we see now as, and it depends on this ratio n over m. Let me write this a little bit more clearly. Okay, so it's e to the minus kn over m. Okay, so if you, and then how I got this was if you solve for k, so if you want to set this to be, so you can kind of plot this as a function of k, and you can find the best, you want this to be as small as possible, and that happens when you get the k is equal to about m over n times the natural log of 2. And I forget I have in my notes that this is the case, but I'm probably not going to work it out here in the spot. But you can write down this probability of false positive. So let's see what happens as you kind of have this balance between m and n here. So if you set k equals to m over n times log n, natural log over 2, I plug this in here, I'm going to get, this is going to be 1 minus e to the negative natural log of 2 to the power k. And so this is going to be 1 minus 1/2 to the k, and you can set this to be, this is 1 over 2 to the k. So it's pretty small. If you set it roughly, if you set k equals to this, you get a probability 1 over 2 to the k probability of a false positive. So you can use this formula in other ways. You can say, well, I want to get this small enough, so I'm going to use the k hash functions. I want to set this to be, I want to set this to occur like 1% of the time. So I guess 1% is hard to get, but so if you set it to be, I guess 2 to the 6 is 60. Wait, 2 to the what is 64? I don't know. So if I set k equals 5, I'm going to get roughly 2% of the time. Is that right? 2, 4, 8, 16, 32. Okay, so roughly 3. If I set k equals 5, I'll get roughly 3% of the time I'll get a false positive, right? And it drops exponentially as I set this up. So I say I want to have 5 of these hash functions. How big do I need to set m in order for this to happen? And then I can figure out, I can solve for m to get a certain probability of false positives. You can kind of go back and forth with this. So these are really, really simple to implement and work very well in very large space. Yeah, okay, so that was all I planned for today. We can talk about other stuff about the class. You can ask me strange questions, or we can kind of leave a little bit early. Yeah, okay, so turn in the clustering homework in a week, and then on Monday next week we'll start a new section on looking at regression. And so Monday will be the lecture where I'll preview like the next 5 lectures by going through all the examples in just 2 dimensions, kind of the techniques we're going to do. And some of them make more sense in high dimensions. So but I'll kind of preview what they look like and all in one picture, and then we'll go through each of them individually. And regression is kind of a large thing where you're fitting kind of some function to a lot of data. Yep.
What's the format of the quiz?
The quiz. Yeah. So the quiz are going to be so the quiz will be open book. It'll be questions that I hope will be easy to finish in the time of the class. Each quiz is worth 5% of your total grade, so it's not too bad. I'm not going to be able to ask you to write code to analyze too much data, but I might be able to say, here's some data. You should run an algorithm. It should look like one of these answers, and you should be able to and explain why, or something like that. I don't plan to make you to try and do any kind of proofs or anything like that, but to try and understand why things work. So it'll be kind of like parts of the homework, but nothing where you have to implement something and nothing where you have to prove something. Is that?
And so we can use the lectures in the book.
Yeah. So I'll have no. So I'm going to have no. You can't open your. You can't have an open laptop, so you can print stuff out. Then you'd print the whole lecture notes. Okay, so maybe I'll have an open laptop too. Let me figure this out. So I really don't want you to print out all the lecture notes. That's probably not a good idea. Okay, so I will. So I'll probably have it. I want to have it open notes, but I don't want you to be like using the internet for stuff. So I don't want you to use Google. I guess then you. Okay. I'll probably allow you to use whatever on your computer. I think you guys are very persuasive. Okay. But it probably won't be useful to use everything. Okay. So, yes. All right. So I'll have more details on that next week about the quiz and what you can use on it.